Okay, so if I'm looking up here, we're going to go ahead and go through a 555 timer backwards because I discovered my YouTube video doesn't have a 555 timer backwards. So I know in this example, and I'm limited on time, that I want to go ahead and use a capacitor. That way I limit myself to 2 variables instead of 3 variables if I wasn't given a capacitor. I like using a 0.47 microfarad capacitor because I do. I'm assigning that the frequency has to be 4 Hertz. I'm assigning that the duty cycle has to be 60%. Remember, if you have a duty cycle that is under 50%, we can't do that with these calculations. We can't do that with the 555 timer. So what we do is we invert that number. So for example, if we wanted 25% duty cycle, we'd go ahead and calculate for a 75% duty cycle. And then we would go ahead and put an inverter after our 555 timer circuit. So a little bit of review there. We have our equations, which you can find plenty of places online, or if you're in my digital electronics class, it's at the end of the 1.2.5 PowerPoint. Those are the equations I'm going to be using as I create this. First thing I'm going to go ahead and do is pull the equation off of there. I know I've used guess technique in other ones. I'm trying to rush through time here. So I'm going to go ahead and pull the equation that time equals 0.693 times R A plus 2RB times C. So right there's my C that I already had there. My time, so if I know my frequency is 4 Hertz, my time is obviously going to go ahead and be the inverse of that. We learned that before in class. My time is going to go ahead and be 0.25 seconds. So if I want to go ahead and plug in the values I know that 0.25 equals, I'm going to leave the labels off for now, 0.693 times RA plus 2RB times my capacitor, which I am going to go ahead and put back into base units. So it's going to be 0.00000047. I'm going to leave the label off again. We could go ahead and sort all the labels off, but for the sake of time, I'm going to go ahead and leave the label off of it so I can calculate this stuff. So now if I want to go ahead and figure this out, I want to go ahead and get either RA or RB by themselves. So what I'm going to do is I'm going to divide this side by this times this. I'm going to divide this side by the same thing. I figure I don't need to do that. Hopefully if you're watching this video, you kind of have the algebra skills for that. So I'm going to punch in my calculator, 0.25, divided by, I'm going to put in parentheses, my 0.693 times 0.00000047. Remember, that's my capacitor size that I went ahead and converted to base units. And I go ahead and calculate that all out, and I find that 767,550, I'm going to round it to 4, this would end up being ohms, is going to equal RA plus 2RB. I'm going to go ahead and leave that for a moment. We have that value, or that equation we could come back to later. I'm going to go ahead and deal with our duty cycle a little bit because we're going to have 2 variables. We have RA and RB that we need to compute for. So I'm going to move over to the duty cycle, go ahead and get RA or RB by itself, and then plug it back in that equation, solve for one, be able to solve for the other. So my duty cycle equation is duty cycle, which our duty cycle we see up here is 60%. As a decimal, that'd be 0.6, so I'm kind of skipping a little bit ahead here. So I'm going to, let's see, DC equals, on the top, RA plus RB all over RA plus 2RB. And then, of course, we have times our 100%, which I take care of when I take this out of a 60% down to the 0.6 I talked about. So I've got my 0.6 equals, while I'm doing this, I'm going to go ahead and do some more math so I'm not just writing a whole line out there. I'm going to have to multiply both sides by the denominator to get that denominator out of there. So I'm going to have 0.6 times, I'm going to put my denominator over here. My denominator on the other side will cancel then. RA plus 2RB equals, now I've still got my numerator over there, RA plus RB. So right there I've gone ahead and combined a couple steps once again for the sake of time, trying to hurry through it. Hopefully we're kind of picking up how I'm doing that, I'm explaining it. I'm going to distribute this 0.6 RA plus 1.2 RB equals RA plus RB. Combine like terms, so I'm going to go ahead and move this 0.6 over here. I'm going to move this RB over here. So 1.2 RB minus RB is going to give me 0.2 RB equals, I'm going to take this 0.6, so I'm going to subtract 0.6 from my whole RA. I'm going to get equals 0.4 RA. And I want to go ahead and get one of these to be 1, so I'm going to divide both sides by 0.2. Divide both sides by 0.2. I can go ahead and see that when I divide both sides, this becomes RB equals 0.4 divided by 0.2. That's the same thing as 2, right? Because the numerator is twice as large as the denominator, equals 2RA. So I've gone ahead and come up with that. I can bring that back over to my equation over here. My RB is going to be replaced with 2RA. So this big number equals RA plus 2 times 2RA. We know that's going to go ahead and be 4RA plus another RA equals 5RA. I can go ahead and take that big number, which I've still got in my calculator, divide by 5, and I go ahead and get that RA is equal to 153,511 ohms equals RA. Now you could round that off a little bit. It doesn't have to be exact, but that would be what our RA is. Now that I've got our RA, I can plug that back into this equation and take it times 2, and I find that my RB would be 307,022 ohms. So just like that, there are 3 values that influence the speed at which our circuit oscillates. We've solved for RA, we've solved for RB, and we're given the capacitor. Those are the 3 things that we can change to influence the speed of our circuit. I know that was a little quick, but hopefully it was helpful.